In the unending quiet of the cosmos, there are tempests. There are rages so immense, so incandescently violent, that they dwarf the sum total of all human conflict, all our wars, our triumphs, and our fleeting passions. These are the outbursts of the universe's true titans, the stars. For millennia we have watched our own star, the sun, believing we understood its moods, its cycles, its occasional fury. We were, it turns out, only watching the slumbering of a giant. We had never witnessed the unbridled rage of a star in its youth, until now. Far across the interstellar void, some 111 light-years away in the ancient constellation of Draco the Dragon, a young star not so different from our own, sun-stirred. Its name is EK Draconis, and what astronomers saw it do has forever altered our understanding of the precarious nature of life in the universe. For the first time in human history, we have captured the image of a coronal mass ejection, a colossal eruption of stellar material from a star beyond our solar system. It was not a flare, it was not a flicker, it was a monster, a celestial dragon breathing a fire of such magnitude it forces us to ask a terrifying new question. In the search for alien life, have we been looking for cradles when we should have been looking for tombs? Could these stellar superstorms be the great executioners of the galaxy, wiping entire worlds clean before life has a chance to truly begin? The story begins not with a bang, but with the patient accumulation of data. Fleets of telescopes, our silent sentinels in the dark, stare into the abyss, collecting photons that have traveled for centuries.
When the magnetic fields
Among
realign,
them, NASA's
they trigger
transiting
what is known as a
exoplanet
coronal
survey
mass
satellite,
ejection.
or TESS, was performing its primary mission, watching for the subtle dimming of stars, the telltale sign of a planet passing in front of its stellar host. But TESS saw something else at EK Draconis. It registered a brilliant preliminary flash, a herald of something more. Simultaneously orbiting high above the blurring effects of Earth's atmosphere, the venerable Hubble Space Telescope was also turned towards the distant star system. Yet the key observation, the one that would reveal the true nature of the event, came from the ground from the Seimei telescope at Kyoto University in Japan. Here, a team of researchers led by Kosuke Namakata and Yuta Notsu was engaged in a meticulous long-term study of stellar activity. They were watching EK Draconis for a specific reason. This star is a near-perfect twin of our own Sun, a G-type yellow dwarf. But it is a twin from a different era. EK Draconis is a cosmic infant, a mere 100 million years old compared to our Sun's dignified middle age of 4.5 billion years. It represents a window into our own solar system's tumultuous past. Watching it is like watching a home video of our Sun as a feral toddler. And on a cold night in April of 2020, that toddler threw a tantrum. The data streamed in first as a superflare, an explosion of light many times more powerful than anything our Sun has produced in recorded history. But the scientists were hunting for bigger game. They were looking for the flare's aftermath, for the eruption's physical substance. They were searching for the coronal mass ejection, the CME. To understand the sheer power of what they found, we must first journey into the heart of a star. Imagine a blacksmith's forge, but one the size of a world. Inside, unimaginable pressures and temperatures fuse atoms together, releasing a torrent of energy. This energy creates a tangled, chaotic web of magnetic fields. Think of these magnetic field lines as colossal elastic bands stretching and twisting through the star's superheated outer atmosphere, the corona. As the star rotates and churns, these bands are pulled taut, twisted into immense high-tension knots, storing unfathomable amounts of energy. Sometimes, a localized knot snaps, releasing its energy as a flash of radiation. This is a solar flare. But a CME is something altogether more profound, more physically devastating. In a CME, an entire archipelago of magnetic loops, a vast continent-sized structure, becomes so twisted and strained that it can no longer hold itself to the star. The magnetic architecture fails on a catastrophic scale. The spring wound for days or weeks finally breaks. The result is the ejection, the physical expulsion of billions, sometimes trillions of tons of plasma, the very substance of the star itself hurled into space. It is a cannonball of electrified gas, a phantom piece of the star liberated and sent screaming across the solar system at millions of miles per hour. We have seen thousands of these events from our own Sunday. They are the source of our beautiful northern and southern lights, but they are also a threat capable of disabling satellites and power grids. What the same telescope saw erupting from EK Draconis, however, was of a different order of being. As the initial superflare lit up their instruments, the astronomers waited. About 30 minutes later, their spectral analysis detected something astonishing. They saw a cloud of hydrogen atoms superheated to millions of degrees, moving times away, times from the star at a blistering 2 million miles per hour. This was the smoking gun. This was the eruption itself. But it was the sheer mass of the ejector that left them breathless. The calculations were checked, rechecked, and checked again. The numbers were undeniable. The coronal mass ejection from EK Draconis carried a mass of more than 10 trillion tons. That is at least 10 times, perhaps as much as 20 times more massive than the largest, most powerful CME ever recorded from our own Sunday. For the first time, humanity had seen the fire of the dragon. The observation was a monumental achievement in astronomy, but with it came a chilling realization. If a star like our Sun in its youth can produce such calamities, what would happen to a planet caught in the crossfire? The answer lies not in abstract theory, but in our own history. We have felt the faintest whisper of this power before. The year is 1859. The world is lit by gaslight and powered by steam. In a small private observatory in Surrey, England, a gentleman astronomer named Richard Carrington is meticulously sketching sunspots. Suddenly, through his filtered telescope, he witnesses 2 patches of blindingly white light erupt from the sunspot group he is drawing. He is the first human to witness a major solar flare in real time. He knew it was significant, but he could not possibly have grasped the consequences. Just over 17 hours later, the Earth was struck. The planet's magnetic shield, the magnetosphere, was violently compressed. Telegraph systems across Europe and North America went haywire. Operators reported sparks leaping from their equipment, setting papers ablaze. Some disconnected their batteries, only to find that the auroral currents in the wires were strong enough to continue sending messages. The spectacle in the sky was even more dramatic. The aurora borealis, typically a high-latitude phenomenon, was seen as far south as Cuba, the Caribbean, and Honolulu. Gold miners in the Rocky Mountains were woken by the brilliant light, believing it to be dawn, and began preparing breakfast. This event, now known as the Carrington Event, was a wake-up call. It was the result of a powerful, but by solar standards not exceptional CME. It struck a world blissfully unaware of its own electrical vulnerability. If a Carrington-level event were to strike our technologically dependent civilization today, the consequences would be catastrophic. Trillions of dollars in damage to power grids, satellite networks, and communications. Widespread, prolonged blackouts. A potential setback of years or even decades. And yet the CME that caused the Carrington event was a mere firecracker compared to the thermonuclear detonation witnessed erupting from EK Draconis.
The EK Draconis event illustrates that for many star systems, the habitable zone is actually a cosmic shooting gallery.
Imagine a world.
The proximity to a volatile star means that despite having the building blocks of life, these planets are routinely sterilized by massive solar flares.
Haven. It has a burgeoning atmosphere, liquid water on its surface,
a calm,
perhaps
the sun.
the first tentative stirrings of prebiotic
We
chemistry.
exist in a
The
rare
first sign
moment of
doom
stellar
would
grace,
arrive at the speed
protected
of light.
by our placid
the
star.
superflare preceding the CME unleashes a torrent of X-rays and ultraviolet radiation. In just minutes, this hard radiation slams into First Haven's upper atmosphere. It ionizes particles, heats the thermosphere to incredible temperatures, and begins to fundamentally alter its chemical composition. For any primitive life on the surface, the UV bath would be intense, capable of sterilizing organisms not shielded by deep water or rock. This, however, is merely the opening salvo. Next comes the storm of high-energy particles, protons accelerated too near the speed of light by the flare's shockwave. This particle storm arrives in under an hour. It is a rain of invisible subatomic bullets. This radiation would be lethal to unprotected life. More critically, it would begin to dismantle the planet's primary defense, its magnetic field, its magnetosphere. Imagine the magnetosphere as an invisible shield, a force field that deflects the constant stream of particles from its star, the solar wind. The proton storm is the first wave of a siege, pummeling the shield, weakening its integrity, and creating holes in its coverage. Satellites would be fried. Any nascent technology would be crippled. But the main assault is yet to come. Days later, the behemoth itself arrives. The 10-trillion-ton cloud of magnetized plasma, the coronal mass ejection, finally reaches First Haven. This is not a wave. It is a tsunami of stellar matter. The impact is an act of cosmic violence on an almost unimaginable scale. The planet's magnetic shield, already weakened, now faces a direct, overwhelming blow. The plasma cloud carries with it the tangled, powerful magnetic field from its parent star. If this field is oriented opposite to the planet's own field, the effect is cataclysmic. A process called magnetic reconnection occurs on a planetary scale. It is as if the shield's defenses are not just breached, but catastrophically short-circuited. Energy equivalent to thousands of powerful nuclear bombs is dumped into the upper atmosphere. Global auroras 100 times brighter than the Carrington events would ignite the sky from pole to pole, a beautiful, terrible death shroud for a world. But the true devastation is more insidious. It is not about the light show, it is about survival. The sheer force of the CME, this relentless plasma wind, begins a process known as atmospheric stripping. It literally sandblasts the planet's air away into space. Particles in the upper atmosphere are energized by the impact and given enough velocity to escape the planet's gravitational pull forever. The process is slow at first, a gradual erosion, but a young, active star like EK Draconis would not produce just one such event. It would produce them frequently, perhaps one every few weeks or every few months. Wave after wave of these super CMEs would wash over the helpless planet. Each impact would peel away another layer of its precious life-sustaining atmosphere. Oceans would begin to boil away into a thinning sky. The surface, now exposed to the full, unfiltered fury of its star's radiation, would be scoured, sterilized, and rendered utterly barren. First Haven, the world of promise, becomes a desolate, airless rock. Its journey towards life is not just halted, it is brutally reversed. The cradle is transformed into a mausoleum. This terrifying scenario raises a profound question about our own cosmic neighborhood. Our sun was once a young star, just like EK Draconis. In its first few 100 million years, it too would have been a raging inferno, lashing out with superflares and titanic CMEs. Did this youthful solar violence shape the destinies of the inner planets? Consider Mars. Today it is a cold, desert world with a whisper-thin atmosphere. But evidence overwhelmingly suggests it was once warmer and wetter, with rivers, lakes, and perhaps even a shallow ocean. It had the ingredients for life. So what happened? Mars, being smaller than Earth, has a weaker gravitational pull. Critically, its internal dynamo died early in its history, causing its protective global magnetic field to vanish. It was left defenseless. It's entirely plausible, even likely, that the young sun's relentless CMEs were the primary culprit in Mars's demise. They stripped away its atmosphere particle by particle over millions of years until the pressure dropped so low that liquid water could no longer exist on its surface. The red planet may be the fossilized evidence of this stellar violence in our own backyard. Venus may have suffered a similar, though different, fate. Its lack of a strong magnetic field left its atmosphere vulnerable. Perhaps the sun's early outbursts stripped away its water vapor, contributing to the runaway greenhouse effect that turned it into the hellscape it is today. Earth, it seems, was lucky. It was large enough to retain a molten core and a powerful magnetic dynamo. Our magnetosphere was strong enough to withstand the onslaught. It bent, but it did not break. Our atmosphere was eroded, but it was also replenished by volcanic outgassing. We survived the sun's fiery childhood, shielded in our magnetic cocoon. The discovery at EK Draconis is therefore not just a piece of stellar trivia. It is a crucial data point in one of the greatest scientific quests of all time, the search for life beyond Earth. For decades, our search has been guided by the concept of the habitable zone, sometimes called the Goldilocks zone. This is the orbital band around a star where temperatures are just right, not too hot, not too cold for liquid water to exist on a planet's surface. We have found thousands of exoplanets orbiting within this zone. Each one is a candidate, a place of hope. But the EK Draconis observation forces a radical revision of this idea. It suggests a second, equally important criterion for habitability, the temperamental zone. A planet might be at the perfect temperature, but if its star is prone to these world-sterilizing outbursts, the Goldilocks zone becomes a death zone. This has enormous implications for where we should be looking. A vast number of the stars in our Milky Way galaxy, perhaps as many as 75%, are not sun-like yellow dwarfs but smaller, cooler red dwarf stars. For a long time, these were considered prime candidates in the search for life. Their sheer number makes them statistically promising, and their incredibly long lifespans, trillions of years, would seem to offer life an almost endless amount of time to evolve. Planets in their habitable zones would be tidally locked, with one side in permanent daylight and the other in eternal night, but it was thought that a thick atmosphere could distribute the heat. However, red dwarfs have a dark side. They are notoriously volatile. They are known to produce frequent, powerful flares, often far more energetic relative to their size than those from sun-like stars. Until now, we had never directly observed a major CME from a red dwarf, but the physics suggests it must happen. The EK Draconis event from a much more stable type of star provides a terrifying benchmark. If a relatively calm young sun-like star can unleash a 10 trillion ton plasma blast, what are the tempestuous red dwarfs capable of? It's likely that the habitable zones around these stars are routinely scoured by super CMEs far more powerful and frequent than the one we just witnessed. Any planet orbiting there would be subjected to a relentless cosmic bombardment. Its atmosphere would be stripped away, its surface sterilized by radiation. The most common star systems in the galaxy might be the most hostile to life. This leads us to one of the most haunting paradoxes in science, the Fermi paradox. The universe is vast and ancient. There are hundreds of billions of stars in our galaxy alone, and hundreds of billions of galaxies in the observable universe. Many of these stars should have planets. The ingredients for life are common. So, as physicist Enrico Fermi famously asked, "Where is everybody? Why is the cosmos so silent?" There are many proposed solutions, but the study of stellar activity suggests a particularly grim one known as the Great Filter. The Great Filter is a hypothetical barrier, a challenge so difficult to overcome that it prevents intelligent life from becoming widespread. Perhaps stellar violence is one of these filters. Maybe the universe is teeming with planets where life begins in the calm oases of their oceans. Maybe simple organisms flourish for millions or even billions of years. But before they can evolve intelligence, before they can reach for the stars, their own sun turns against them. A series of super CMEs like the one from EK Draconis strips their world of its air and water, erasing billions of years of evolutionary progress in a geological blink of an eye. Life in this model is not rare because it is hard to start. It is rare because it is so easy to extinguish. Our own existence then becomes a testament to extraordinary luck. We orbit a G-type star, one of the more stable varieties. We arose late in our star's life, after its youthful tantrums had subsided. Our planet was large enough to generate a protective magnetic field. We navigated a cosmic minefield and emerged for now unscathed. The silence of the cosmos might not be the silence of an empty room. It might be the silence of a graveyard. This first ever observation of an extrasolar CME is therefore a moment of profound dualism for science. It is a triumph of human ingenuity. The coordination of multiple telescopes, the painstaking analysis, the ability to see the weather on a star over 100 light-years away, it is a staggering achievement. It opens a brand new field of study, exoplanetary space weather. We are no longer limited to studying our own star. We can now begin to map the behavior of thousands of others. Future observatories like the James Webb Space Telescope can study the atmospheres of exoplanets for the chemical signatures of stripping. We can hunt for ozone, a gas easily destroyed by stellar particle events. By observing a planet's atmosphere over time, we might be able to see it diminishing to witness this process of planetary destruction in real time. We can finally start to build a true statistical understanding of which star systems are genuine havens and which are cosmic mirages. But this triumph is also a deep and humbling caution. It is a reminder of the sheer indifferent power of the universe. We look out into the void and see beauty and wonder. But the cosmos is not a tranquil garden designed for our benefit. It is a violent, chaotic, and often lethal place. The same stellar fires that warm worlds and power photosynthesis can also turn and devour their creations without a moment's thought. The forces at play are beyond our comprehension, and our grip on existence is fragile. The light from EK Draconis' eruption travelled for 111 years to reach us. It left its source around the year 1909, when Einstein was just beginning to formulate his theory of general relativity, when our understanding of the cosmos was in its infancy. For over a century, this silent scream of plasma has been hurtling through space, a message in a bottle about the true nature of stars. Now we have received that message. It tells us that our sun, our serene, life-giving star, carries within it the memory of a violent past. It warns us that many of the worlds we have identified as potentially habitable may in fact be cosmic killing fields, sterilized by the fury of their parent stars. And it forces us to look at our own world with new eyes, to appreciate the delicate balance of forces that allows us to be here, the strength of our magnetic field, the stability of our middle-aged star, the immense good fortune of our cosmic address. We have, for the very first time, caught a glimpse of a celestial dragon's fire. In its terrifying, beautiful, and world-destroying glare, we see not the certainty of our doom, but the almost unbelievable preciousness of our own quiet dawn. The search for life will continue. But now it continues with a new awareness. An awareness that finding a world that is just right is not only about finding a place that is warm enough, it is about finding a place that is safe enough, a place sheltered from the rage of the Titans. A place that has against all odds survived the fire.